On March 19, 1945, just 50 miles off the coast of Japan, Lieutenant Commander Joseph O'Allahan tightly gripped the steel railing. The USS Franklin shuddered beneath another explosion, the 23rd in under an hour. Through the thick, black, choking smoke that poured from every doorway and hatch, he watched the sailors. They were aiming fog nozzles into the inferno that had consumed the hangar deck. 3 years earlier, naval officers would have laughed at the thought of using what looked like garden sprayers to fight a fuel fire on an aircraft carrier. Yet today those very fog nozzles were all that stood between 700 men and certain death. The story of how a rejected idea from a New York City firefighter became standard equipment on every United States Navy. Warship is one of the most remarkable transformations in military history. It didn't begin with engineers or admirals, but with men who fought fires in dockside warehouses and tenement buildings. Men who understood that sometimes the smallest droplets of water could achieve what torrents could not. What none of them knew in those early days was that their persistence in the face of institutional rejection would ultimately reshape naval warfare itself, not only saving thousands of lives and hundreds of ships, but also creating firefighting doctrine that would endure for more than half a century. The crisis at sea. Pearl Harbor's lesson to understand this transformation, we must return to the crisis that began 4 years prior, on a Sunday morning that fundamentally changed everything.
The Navy thought it knew about fighting fires at sea. The
crisis that would compel the Navy to reconsider everything it knew about fighting. Fires at sea began on December 7, 1941, when Japanese aircraft struck Pearl Harbor that Sunday morning. They ignited fires that exposed a terrible truth about American naval preparedness. The sheer scale of the disaster was unprecedented. In less than 2 hours, the Pacific Fleet suffered catastrophic losses that would reshape American naval doctrine for generations. The battleship Arizona exploded and sank in 9 minutes. Her forward magazine detonated with such force that the blast wave was felt across Oahu and shattered windows miles away. The explosion lifted the 33,000-ton vessel partially out of the water before she settled back and began her final plunge. More than 177 men died, most of them trapped below decks. Fire and flooding overwhelmed damage control parties who lacked the training and tools to save their ship. The forward magazine explosion was so powerful that it broke the ship's back, sending the bow section plunging to the harbor bottom, while fires consumed everything after the break. Oklahoma capsized in 12 minutes, slowly rolling to port after torpedo struck her hull. 429 men were trapped inside as the battleship turned turtle, her bottom exposed to the sky. Hundreds of sailors pounded desperately on the hull from within. Rescue parties could hear them for days, cutting through steel with acetylene torches in a frantic race against rising water, asphyxiation, and time inside the inverted compartments. Some men were saved, but most perished in the darkness. West Virginia settled into the harbor mud, her decks ablaze with burning oil spilled from ruptured fuel tanks. The fires burned for approximately 30 hours, fed by oil floating on the water's surface and petroleum vapors rising from damaged tanks throughout the ship. Firefighting teams desperately fought to contain the flames, but lacked the techniques and equipment needed to extinguish fires burning on water or cool superheated spaces filled with petroleum vapor. Flooding spread through compartments damaged by bombs and torpedoes, and the ship slowly settled over 3 days, eventually coming to rest on the bottom, with only her superstructure visible above water. 106 men were killed. California burned as she slowly sank over a 3-day period. Raging fires consumed her superstructure while water steadily rose through her lower compartments. A bomb and 2 torpedoes had opened her hull to the sea, but flooding was not the only issue. Fire was as much to blame for dooming her. 104 men were killed and 61 wounded as firefighting teams struggled unsuccessfully to contain both elements. The ship finally settled to the bottom with her decks awash, another victim of inadequate firefighting capability. Nevada became the only battleship to get underway during the attack, her crew desperate to escape the inferno of Battleship Row. However, fires from strafing runs and bomb hits spread faster than her damage control parties could contain them. With flames threatening to reach her magazines and create another catastrophic explosion like the Arizona's, Her captain made the agonizing decision to beach the ship rather than risk blocking the harbor channel. Nevada ran aground off Hospital Point, still burning, her attempt at escape thwarted by fires that could not be controlled. The pattern was clear and damning. In a single morning, the United States Navy lost more ships to fire and its secondary effects than to direct enemy action alone. Torpedoes and bombs started fires, but it was the Navy's inability to control those fires that transformed survivable damage into total loss. Ships that should have been saved were instead consumed by flames that spread unchecked through steel corridors, overwhelmed damage control parties armed with obsolete techniques and inadequate tools, and ignited ammunition magazines. A firefighter's expertise, Lieutenant Harold J. Burke. Among those who studied the disaster with particular interest was Lieutenant Harold J. Burke, a Navy reservist who, before being called to active duty, had spent 20 years with the New York City Fire Department. His path to this moment had been shaped by decades of brutal experience fighting fires in one of America's most demanding urban environments. Harold J. Burke joined the FDNY in the early 1920s, entering a fire service still dominated by techniques that had changed little since the previous century and by horse-drawn apparatus. New York in those years was a city of extremes, gleaming skyscrapers rising in Manhattan, alongside tenements packed with immigrants on the Lower East Side, warehouses stuffed with combustible. Materials lined the waterfront while modern department stores filled with the latest goods. Working his way up through the ranks during a transformative period in American firefighting, Burke fought blazes in 5-story walk-up tenements, buildings with wooden interior construction that burned like kindling once fire took hold, where families lived packed 20 to a floor. He also battled warehouse fires, where industrial chemicals and burning turpentine paint created infernos that conventional firefighting methods could barely touch. Through these experiences, he learned that different fires required different approaches. What worked on burning wood might spread flames through burning liquids, and that sometimes less water applied correctly accomplished more than a torrent applied incorrectly. By the time war clouds gathered in the late 1930s, Burke had risen to deputy chief of the FDNY, one of the most demanding firefighting positions in America. As deputy chief, he oversaw operations across multiple boroughs, developing standardized procedures that could be applied consistently across the department and coordinating responses to major fires. He was responsible for tactical doctrine, equipment acquisition, and training, experience that would prove invaluable when applied to naval firefighting. The FDNY of Burke's era was at the forefront of firefighting innovation. Municipal fire departments fought fires daily, learning through painful experience what worked and what failed. They refined techniques, experimented with new equipment, and shared knowledge across departments. By 1940, progressive fire departments had largely adopted fog nozzles for specific applications, particularly for fires involving flammable liquids, where solid streams proved not just ineffective, but actively dangerous. Burke had witnessed firsthand how fog nozzles transformed outcomes in industrial fires. He had seen petroleum fires that conventional tactics couldn't touch extinguished by the steam-generating capability of properly applied water fog. He had watched burning warehouse fires that solid streams only spread brought under control within minutes once fog patterns were applied. His understanding of the physics of heat absorption and steam generation, the tactical applications of indirect application and water curtains, and the importance of cooling superheated gases before attempting interior attacks, set him apart from officers whose knowledge came purely from naval tradition. Tradition versus necessity. When Burke reported for active duty with his commission as a Navy lieutenant, he brought with him this wealth of practical knowledge. His initial assignment was to inspect damage control procedures aboard ships in port, evaluating their readiness for combat operations. What he found alarmed him profoundly. Naval firefighting in 1941 remained rooted in traditions established during the Age of Sail. The basic approach had changed remarkably little over centuries. When fire broke out, sailors formed bucket brigades to pass water hand to hand from the nearest source. When pumps were available, they directed solid streams of water at the base of flames through straight-bore nozzles that had barely evolved since the 1800s. The emphasis was on volume. Pour enough water on any fire, and eventually it must go out. This doctrine worked adequately for the fires most likely to occur on wooden ships. Fires in crew quarters or storage spaces, smoldering rope, burning canvas, which were generally contained within compartments that could be sealed off and involved ordinary combustibles that responded to cooling from water. Application. Naval tradition emphasized aggressive interior attacks, overwhelming flames with sheer volume of water, and getting as close to the fire as possible with the largest hose capable of fitting through passageways. But modern warships bore little resemblance to their wooden ancestors. Steel construction meant fires behaved differently, with metal conducting heat throughout structures and creating superheated spaces that were death traps for firefighters. The introduction of aviation operations on carriers brought massive quantities of aviation gasoline aboard, stored in tanks distributed throughout the ship and pumped through miles of piping to fueling stations on flight and hangar decks. A single carrier might carry over 150,000 gallons of aviation gasoline along with ammunition and bombs for dozens of aircraft. The vulnerability this created was staggering, yet the Navy's firefighting doctrine had not evolved to match the threat. Inspecting ships equipped with fire mains and hydrants positioned throughout, Burke found straight-bore nozzles of various sizes, from small handheld types to massive monitors capable of delivering thousands of gallons per minute. He observed damage control parties trained to stretch hoses, connect to hydrants, and direct solid streams at fires. What he did not find was any recognition that solid streams were fundamentally inadequate for the types of fires modern naval warfare would create. When he questioned damage control officers about procedures for fighting aviation gasoline fires, he received answers that revealed dangerous ignorance. They would direct solid streams at the base of flames, they explained, overwhelming the fire with volume. When Burke pointed out that solid streams scatter burning gasoline and spread fire rather than extinguishing it, he was met with irritation at civilian interference with naval traditions or blank stares. The Navy's damage control schools taught bucket brigade procedures unchanged since wooden ships. They emphasized the importance of maintaining pressure in fire mains, of efficiently organizing men to stretch hoses, and of directing streams at the seat of fire. They taught almost nothing about the behavior of different types of fires, about the physics of heat transfer and steam generation, about the dangers of applying water to burning liquids, or about the importance of cooling superheated spaces before entry. Burke submitted report after report documenting these deficiencies, recommending modernized training and the adoption of fog nozzles. His reports were filed away, acknowledged with perfunctory responses, but producing no actual changes. The Navy had been fighting fires the same way for generations. Why should they change now based on the recommendations of a civilian firefighter who had never served at sea? Compiling the evidence, the cost of inaction, then came Pearl Harbor, and everything changed. In the days and weeks following December 7th, damage assessment teams fanned out across Pearl Harbor to document what had happened and why. They interviewed survivors, photographed destroyed ships from every angle, examined burned compartments, and attempted to reconstruct the sequence of events that had turned survivable damage into catastrophic loss, obtaining copies of these reports and photographs. Through his position in the Navy's Damage Control Assessment Office, Burke saw confirmation of his worst fears. Ship after ship showed the same pattern. Initial damage from bombs or torpedoes was followed by fires that spread out of control, overwhelming damage control parties, and ultimately dooming vessels that should have survived. The photographs told stories of tragic failure and desperate improvisation. Firefighting teams had attacked fires with solid streams, only to watch flames spread as water scattered burning oil across decks and into adjacent compartments. They had directed powerful streams into burning spaces, only to create so much flooding that ships sank or capsized before fires could be controlled. They had been driven back again and again by smoke and heat they had no way to dissipate or cool, forced to watch helplessly as flames consumed their ships. Survivor accounts provided even more damning evidence. Sailors described pouring thousands of gallons into burning spaces with the largest hoses they could deploy, only to watch flames intensify as water pressure scattered burning petroleum. They described being unable to approach within 50 feet of fires because radiant heat was too intense, unable to cool spaces enough to make entry. They described ammunition cooking off because they had no way to cool magazines threatened by adjacent fires, explosions that spread fire to new areas and killed firefighting personnel. Most tellingly, they described the psychological impact of facing fires they had no effective means to fight. Training had taught them that solid streams were the answer to any fire. When those streams failed, and fires grew despite their efforts, sailors experienced a profound sense of helplessness. Some prematurely abandoned firefighting efforts, convinced nothing could stop the flames. Others persisted beyond the point of safety, dying in futile attempts to control fires with inadequate tools, compiling this evidence into a comprehensive report arguing for the complete overhaul of naval firefighting. Training and immediate adoption of fog nozzles. Burke documented municipal firefighting experience with similar fires. He provided data on fog nozzle effectiveness against burning petroleum, outlined a training program that could transform naval damage control capabilities within months, and explained the physics of why fog patterns succeeded where solid streams failed. His report landed on desks throughout the Bureau of Ships and the Navy's Training Command. Once again, it was met with skepticism bordering on hostility. Officers questioned whether municipal firefighting experience was relevant to shipboard conditions. They argued that fog nozzles looked inadequate, that the fine mist appeared to be less water and therefore less effective. They suggested that better training in traditional methods was all that was needed, not wholesale equipment changes. The institutional resistance Burke faced was rooted in multiple factors. Adopting his recommendations would require admitting that Pearl Harbor losses were partly due to inadequate doctrine, not just surprise attack. It would mean replacing equipment fleet-wide at significant cost. It would require retraining thousands of sailors and rewriting training manuals. Most fundamentally, it would challenge naval traditions that stretched back centuries, traditions that defined professional pride and institutional identity. Burke's recommendations were revolutionary, and revolutions are never welcomed by established institutions, even when evidence demands change. Finding himself fighting cultural inertia, bureaucratic self-protection, and the natural human resistance to admitting error, Burke continued his battle. The toll continues, Lexington and Wasp, while Burke fought his bureaucratic battles. The war continued and ships continued to burn. Each new loss provided fresh evidence that traditional firefighting methods were inadequate, but also created pressure to focus on building new ships rather than changing how fires were fought on existing ones. On May 8, 1942, the carrier Lexington succumbed to uncontrolled fires following damage at the Battle of Coral Sea. The carrier had survived multiple bomb and torpedo hits during the battle, damage that was serious but should have been survivable. Her damage control parties initially fought the fires successfully, and for several hours it appeared the ship might be saved. Then, fuel vapors that had accumulated in compartments damaged by torpedoes found an ignition source, triggering a massive explosion that started fires deep in the ship's interior. Firefighting teams attacked these new fires with solid streams, but the flames were fed by leaking hydraulic fluid and aviation gasoline that solid streams could not effectively extinguish. Heat built up in compartments adjacent to the fires, starting secondary fires faster than crews could contain them and cooking off ammunition. Within hours, fires were burning out of control through multiple decks. Explosions rocked the ship as magazines detonated. 216 men died before Lexington had to be abandoned and scuttled. A capital ship, one of only 4 fleet carriers available to the Pacific Fleet, was lost not to enemy action alone, but to the Navy's inability to control the fires that followed initial damage. On September 15, 1942, the carrier Wasp was torpedoed by Japanese submarine I-19, southeast of San Cristobal Island in the Solomons. 3 torpedoes struck the carrier's starboard side, rupturing aviation gasoline tanks and starting massive fires on the hangar deck. Aviation gasoline poured from ruptured tanks, creating pools of burning fuel that spread into adjacent spaces and across the hangar deck. DC parties directed solid streams at these fires, but the high-pressure water scattered burning gasoline, spreading flames rather than extinguishing them. Within 30 minutes, fires were burning on 3 decks. Ammunition began cooking off, preventing close approach to the fires and killing damage control personnel. The ship lost electrical power, meaning pumps could not maintain adequate pressure in fire mains. Firefighting teams continued fighting with reduced water pressure, but solid streams that were barely effective at full pressure accomplished nothing at half pressure. Heat built to levels that began warping steel structures. After 3 hours of futile firefighting efforts, the order was given to abandon ship. 193 men were killed. Wasp was scuttled by destroyer torpedoes. Another carrier lost to fires that should have been controllable. The pattern repeated with smaller vessels. Destroyers hit by bombs or torpedoes found their damage control parties overwhelmed by fires that spread faster than they could be contained. Cruisers survived torpedo hits only to be consumed by fires that traditional methods could not control. The close quarters on destroyers meant fires could reach magazines within minutes, creating catastrophic explosions. Each loss provided more evidence that Burke's warnings were correct. But institutional inertia continued to prevent change. An ally in a demonstration by late 1942, the mounting toll of ships lost to fire was becoming impossible to ignore. Admiral Ernest King, Commander-in-Chief of the U.S. Fleet, demanded answers about why so many damaged ships were being lost to fire rather than saved by damage control. His inquiries put pressure on the Bureau of Ships to produce results, to explain why the Navy seemed unable to control fires that municipal fire departments routinely handled. This created an opening for Burke, but he needed an ally with sufficient authority to force change through bureaucratic resistance. That ally came in the form of Rear Admiral Edward L. Cochrane, who took over as Chief of the Bureau of Ships on November 1, 1942. Cochrane was a 1911 Naval Academy graduate and an engineer by training who had specialized in propulsion systems and ship construction throughout his career. Unlike many flag officers whose experience was primarily operational, Cochrane understood technical systems at a deep level. He had earned a reputation for willingness to challenge conventional wisdom when engineering principles demanded it, and for innovation. Cochrane's appointment came at a critical moment. The Navy was in the midst of the largest shipbuilding program in history, with hundreds of new vessels under construction, but ships being lost to fire at sea threatened to undermine this massive investment. Cochrane immediately demanded a comprehensive review of damage control capabilities, particularly firefighting training and equipment. Seeing his opportunity, Burke arranged a meeting with Cochrane through intermediaries to present his case for fog nozzles. The meeting did not go as Burke initially expected. Cochrane listened to Burke's arguments about fog nozzle superiority, then peppered him with technical questions that revealed a sophisticated understanding of heat transfer, fluid mechanics, and thermodynamics. What were the optimal droplet sizes for different fire conditions? How exactly did fog patterns increase heat absorption rates? How did steam generation rates compare between solid streams and fog at various pressures? Burke answered each question, providing practical examples from his FDNY experience, not just theoretical explanations. He described specific fires where fog nozzles had succeeded after solid streams failed, explained the tactical applications in different scenarios, and acknowledged the limitations of fog nozzles in situations where solid streams remained superior. Cochrane was impressed by Burke's practical experience and his command of technical details, but he remained skeptical. The fine mist of the fog nozzle looked inadequate. How could something that appeared to deliver less water actually be more effective? Burke explained the physics of heat absorption and surface area, but Cochrane needed more than explanations. He needed proof. "Lieutenant," Cochrane told Burke, "the Navy doesn't change doctrine and equipment based on municipal experience and theories. If you want me to consider this seriously, you need to demonstrate that fog nozzles actually work better than solid streams under controlled conditions where we can measure results." Burke immediately agreed. "Give me a week to set up a demonstration, Admiral. I'll prove it works." Burke spent the next week preparing the most important demonstration of his life. He arranged for a controlled burn facility at a naval yard where realistic fires could be created safely. He obtained aviation gasoline, the same 100-octane fuel that created the most dangerous fires at sea and powered carrier aircraft. He built a mock-up compartment that replicated the limited ventilation, confined spaces, and steel construction found aboard ship. He assembled damage control equipment, several rockwood fog nozzles, and straight-bore nozzles of various sizes. He recruited experienced firefighters from both Navy damage control schools and the FDNY to serve as operators, ensuring that any differences in results would be due to equipment, not operator skill. Most critically, he installed measurement instruments to quantify results objectively. Thermocouples placed throughout the compartment would measure temperatures before, during, and after water application. Timers would document how long it took to achieve complete extinguishment and knockdown. Flow meters would record exactly how much water was used. Burke wanted data that could not be dismissed as subjective opinion. The undeniable proof Cochrane arrived for the demonstration, accompanied by several senior officers from the Navy's Training Command and the Bureau of Ships. Some were genuinely interested in seeing Burke's claims validated or refuted. Others attended, expecting to witness the failure of civilian meddling in naval traditions, looking forward to dismissing fog nozzles once and for all. Burke began with a presentation explaining what they would witness. "Gentlemen, we will conduct 3 burns in this compartment. The first will be extinguished using standard Navy damage control equipment, a $2 Frac 1 2-inch solid stream, operated by experienced personnel. The second will be extinguished using a fog nozzle on the same size hose, operated by equally experienced personnel. The third will be a side-by-side comparison with both methods attempted simultaneously. In each case, we will ignite 20 gallons of aviation gasoline, enough to create a serious fire, but small enough to be safely controlled." The first burn began. Aviation gasoline was spread across the steel deck and ignited, creating an instant inferno that filled the compartment with black smoke and flames. The heat was intense. Observers standing 20 feet from the compartment entrance could feel radiant heat on their faces. A damage control team wearing protective gear advanced with a solid stream, directing high-pressure water at the base of the flames. The result was exactly what Burke had predicted. The high-pressure stream hit the burning gasoline and scattered it, spreading fire across a wider area. Some of the water simply ran off as waste, passing through the flames without absorbing much heat. Visible flames diminished slightly where the stream directly impacted, but flared higher in areas where scattered gasoline found new fuel sources. After 2 minutes of continuous application, the fire was still burning across most of the compartment floor. After 5 minutes, it was finally out, but the compartment was flooded with several inches of water. Temperatures remained dangerously high, and the method had clearly struggled to control a relatively small fire. "Note the time to extinguishment," Burke told the observers. 5 minutes, 7 seconds. Note also the water usage, 420 gallons. Note the compartment remains too hot for safe entry, over 400 to circaf, and note the flooding, which on a damaged ship could contribute to stability problems. The second burn used the same fuel load in the same compartment, now dried and prepared for another test. This time, Burke's team advanced with a fog nozzle, setting it to a wide-angle fog pattern. They directed the fog not directly at the flames, but slightly above them, creating a blanket of water droplets that fell through the fire zone while simultaneously cooling the superheated air and smoke in the upper part of the compartment. The effect was dramatic. Within 30 seconds, flames visibly diminished throughout the compartment. Within 60 seconds, they were reduced to small pockets. Within 90 seconds, the fire was completely out. Burke's team then swept the fog pattern across the bulkheads and overhead, cooling the entire space. When they emerged, thermocouples showed compartment temperature had dropped from over 1200 T-circulav to less than 300 T-circulav. "Time to extinguishment," Burke announced. 1 minute, 32 seconds. Water usage, 75 gallons. Compartment temperature reduced to safe entry levels. Minimal flooding. This is the difference, gentlemen. The fog pattern provides vastly more surface area for heat absorption, converts water to steam more efficiently, and achieves better results with less water. The third demonstration put both methods side by side. 2 teams entered the burning compartment simultaneously, one with a fog nozzle, one with a solid stream. The fog team achieved knockdown in under a minute. The solid stream team was still fighting scattered pockets of fire 3 minutes later when the exercise was terminated. Cochrane had seen enough. The data was undeniable. Fog nozzles extinguished the fires faster with less water and left spaces safer and cooler. The visual difference was equally compelling. What had looked like inadequate mist had proven far more effective than impressive-looking solid streams. "Lieutenant Burke," Cochrane said, "I'm convinced. The question now is how fast we can re-equip the fleet and retrain our sailors." Several of the other officers present tried to raise objections. Fog nozzles might work in controlled conditions, but would fail in combat chaos. Sailors could not be trained to use them effectively. The cost of re-equipping hundreds of ships was prohibitive, but Cochrane cut them off. "I just watched fog nozzles extinguish fires 3 times faster using 1/5 the water. Every day we delay adopting this equipment, we risk losing more ships and sailors to fires that could be controlled. We're implementing this immediately. Lieutenant Burke, you're hereby tasked with establishing a fleet-wide training program. You'll have whatever resources you need." Immediately facing the challenge of transforming his demonstration into a fleet-wide training program, Burke confronted an enormous task. Thousands of sailors needed training. Hundreds of instructors needed to be prepared. Dozens of training facilities needed to be built. Traditional military training timelines, the measured pace of military transformations, which usually takes years, was not an option for Burke. He had at best months before the fleet needed these skills in combat. His first action was to recruit assistants. Through Navy personnel channels, Burke identified Lieutenant Kilduff, a reservist who, before the war, had served with the Boston Fire Department. Kilduff brought experience as both a training instructor, having run the Boston FD's recruit academy for several years, and as a firefighter. Together, Kilduff and Burke formed the foundational team that would revolutionize naval damage control training. Their approach was, for the military training of that era, revolutionary. Instead of limited practical exercises following classroom instruction, Burke and Kilduff designed a program centered on realistic fire training. This put sailors into conditions as close to actual shipboard fires as safety would permit. They believed that experience was the source of confidence, and that sailors who had successfully fought realistic training fires would perform effectively in combat. The first training facility opened at the Navy's K Street Annex in South Boston, at the Boston Naval Yard in June 1942. Kilduff and Burke spent weeks designing and constructing the training props. They constructed full-scale mock-ups of ship compartments using steel decks, bulkheads, and overheads salvaged from scrapped vessels. These compartments replicated the limited access, confined spaces, and restricted ventilation found aboard a ship. They installed realistic fire scenarios using controlled fuel burns that could create intense smoke and heat without endangering students beyond acceptable limits. The centerpiece was a hangar deck mock-up that could simulate an aviation gasoline fire, such as those that had doomed Wasp and Lexington. The structure was 30 feet wide and 50 feet long, with a steel deck, and fuel delivery systems that could create pools of burning gasoline across the deck, along with overhead ventilation systems that could be secured to replicate battle damage. Safety systems included escape routes, fire suppression systems, and emergency cutoffs, but students experienced realistic smoke, heat, and flames. Other training props included a berthing compartment with burning Class A combustibles, an engine room mock-up with fuel oil fires, a series of small compartments for teaching basic firefighting techniques. Each prop was instrumented, allowing instructors to monitor conditions and ensure safety, while still pushing students to their limits. The training curriculum developed by Kilduff and Burke systematically progressed from basic to advanced skills. Day 1 started with classroom instruction on the theory behind fog nozzles, the physics of heat transfer and fire behavior. Students learned how to adjust nozzles for different conditions, why fog patterns worked, and when solid streams remained the better choice. However, classroom time was limited to 4 hours. The rest of the day was hands-on training. Students suited up in protective gear, heavy canvas jackets, gloves, helmets. They learned to check equipment, to work in teams, and to don emergency breathing apparatus. Then they entered the small compartment trainer for their first live fire. Instructors ignited a controlled burn, and students practiced achieving complete extinguishment, advancing as the fire diminished, applying fog patterns from a safe distance, and approaching the fire. The evolution was repeated multiple times until movements became automatic. Day 2 escalated the intensity. Students faced larger fires in more realistic scenarios. They practiced advancing hose lines through smoke-filled passageways. They learned to force entry through doors blocked by pressure and heat. They experienced flashover conditions, when superheated gases in a compartment simultaneously ignite, in a controlled environment where instructors could demonstrate how cooling overhead gases with fog patterns prevented flashover. The training was demanding, both physically and mentally. Visibility was reduced to zero by smoke. Temperatures in training compartments reached $500 circ to $600 circ F. Students learned to trust their training, to work by feel, and to function in conditions of extreme stress. While many found it terrifying at first, instructors pushed them through fear to competence. Day 3 brought the full scenario. Fighting a simulated hangar deck fire with aviation gasoline burning, simulated casualties requiring rescue and smoke filling the space. Students worked in teams, coordinating multiple hose lines, with some advancing to directly attack flames, while others applied fog to cool spaces. They learned to maintain discipline under conditions approaching actual combat, to support each other, and to communicate in zero visibility. The transformation was remarkable. Sailors who arrived frightened or skeptical, having never fought a fire in their lives, left confident, having repeatedly knocked down intense fires using techniques that worked. Many later reported that combat fires, while more dangerous due to actual casualties and enemy action, were psychologically easier because they had experienced similar conditions in training. Burke and Kilduff personally trained the first cadre of 260 instructors through an intensive 3-week program. These instructors would fan out to establish firefighting schools at every major continental naval base. The selection criteria for instructors were demanding. They needed teaching ability, firefighting experience, leadership skills, and technical understanding. Many were drawn from municipal fire departments, reservists like Kilduff and Burke, who brought civilian expertise into military service. The instructor training program covered not just firefighting techniques, but student evaluation, prop maintenance, safety procedures, and teaching methods. Burke emphasized that instructors needed to balance safety with realism to push students hard enough to build real confidence without creating unnecessary risk. He shared lessons from his FDNY experience about building muscle memory through repetition, about teaching firefighting skills, and about how to overcome the psychology of fear. As instructors dispersed to other bases and graduated, the program was replicated systematically. The San Diego Naval Base opened its firefighting school in August 1942. Norfolk followed in September. By the end of 1942, firefighting schools were operating at a dozen other major bases, including Charleston, Great Lakes, Seattle, and Pearl Harbor. Each school used identical training props built to Burke's specifications, ensuring consistency fleet-wide. This standardization was critical. A sailor trained in Boston used identical tactical approaches, equipment, and techniques to one trained in San Diego. When ships from different squadrons operated together, the damage control parties could coordinate seamlessly. Officers could assume that any properly trained sailor would respond to fires using proven methods, allowing for predictable coordination and planning during battle damage situations. The training program expanded to include officers in dedicated courses covering damage control, firefighting tactics, coordination, and leadership during fire emergencies. Burke insisted that officers understand not just what to order, but why, so they could evaluate firefighting effectiveness and make informed decisions under pressure. Officer training included tabletop exercises where they managed multiple simultaneous fires, made triage decisions about which fires to fight first, and allocated resources. By mid-1943, the training program was yielding results. Thousands of sailors had been trained in fog nozzle techniques. Ships deploying to combat theaters carried crews confident in their ability to fight fires effectively. The psychological transformation was as important as the technical skills. Sailors no longer viewed fire as an overwhelming force, but as an enemy they had been trained to defeat. Equipping the fleet and early combat validation training alone would not save ships. The fleet needed fog nozzles in sufficient quantities to equip every vessel, and production needed to happen quickly despite wartime manufacturing constraints. The Bureau of Ships moved aggressively to contract for fog nozzle production, placing orders with multiple manufacturers to build redundancy into the supply chain and ensure rapid delivery. The Rockwood Sprinkler Company became the primary contractor for the Rockwood all-purpose fog nozzle, the design Burke had championed. The company's factory in Worcester, Massachusetts, geared up for mass production, adding shifts and hiring additional workers to meet Navy demands. By early 1943, Rockwood was producing thousands of nozzles monthly. The Bureau of Ships standardized on two sizes, nozzles for 1.5-inch hose and nozzles for 2.5-inch hose. This simplified training and logistics. Every ship would carry both types, with the larger for major fires and the smaller nozzles for general use. The three-position design, fog, solid stream, and shutoff, gave sailors tactical flexibility. Extension applicators allowed firefighters to reach into spaces too dangerous for direct entry, directing fog through ventilation openings or doorways. Manufacturing the nozzles required precision machining. The internal mechanisms that broke water into fog patterns needed to be manufactured to tight tolerances to function reliably at the required flow rates and pressures. Quality control was critical. A nozzle that failed in combat could cost lives. Rockwood implemented rigorous testing, visually inspecting fog patterns and pressure testing each nozzle before shipping. Distribution logistics challenged the Navy's supply system. New construction ships were easiest, with fog nozzles installed as part of initial damage control equipment packages. Ships already in service needed retrofitting, which meant delivering nozzles to forward bases where ships operated. The Navy established dedicated supply channels for damage control equipment, prioritizing fog nozzles for rapid distribution. Supply ships carried fog nozzles to forward anchorages at Ulithi, Eniwetok, and Pearl Harbor. Ships pulled into these bases for maintenance and resupply received fog nozzles as a priority item. By late 1943, most frontline combatants had received at least partial equipment. By mid-1944, coverage was nearly universal. The transition from solid streams to fog nozzles was not absolute. Traditional solid-bore nozzles remained aboard as backup equipment and for specific applications where they retained advantages. Solid streams were superior for certain scenarios, such as firefighting from a distance, cooling structures externally, or when maximum reach was needed. Burke had never advocated eliminating solid streams entirely, only ensuring that fog nozzles were available. As the primary tool for the most dangerous shipboard, fires, damage control stations, throughout ships were reconfigured to store fog nozzles, prominently with cleaning equipment, spare parts, and extension applicators. Maintenance procedures were taught and developed. Fog nozzles required regular cleaning to prevent salt buildup that could clog the fine passages that created fog patterns. Sailors learned to clean, disassemble, and reassemble nozzles, and to periodically test them to identify and replace worn parts. The material cost of equipping the fleet was substantial, but not prohibitive. Fog nozzles were relatively inexpensive compared to other naval equipment. Each nozzle cost approximately $75 compared to millions for major weapon systems. A destroyer might carry 20 nozzles for a total equipment cost of $1,500. A carrier might carry 60 for $4,500. Across the entire fleet, the total investment was measured in hundreds of thousands of dollars, trivial compared to ship construction costs and inconsequential compared to the value of lives and ships saved. The early successes, 1943-1944. The first combat tests of Burke's program came in scattered incidents throughout early 1944 and 1943. Ships took damage, fires erupted, and damage control parties trained in fog nozzle techniques saved vessels that might otherwise have been lost. Each success reinforced the value of the equipment and training transformation and built confidence. In November 1943, the light cruiser Birmingham took a torpedo hit that ruptured fuel tanks and started fires in 2 engineering spaces. DC parties attacked the fires with fog nozzles using indirect application through ventilation ducts to cool spaces too hot for direct entry. The fires were controlled within 40 minutes, and Birmingham continued operations after temporary repairs. Previous doctrine would likely have required flooding the compartments, potentially dooming the ship. Fog nozzles provided a more effective alternative. In January 1944, The destroyer Spence survived bomb hits during operations in the Gilbert Islands. The bombs penetrated the main deck and exploded in crew berthing areas, starting fires that spread rapidly through the bedding and wooden furniture that filled these spaces. Firefighting teams used fog patterns to cool adjacent spaces and prevent fire spread while attacking the main fire directly. The combination of minimal water usage and rapid knockdown allowed Spence to maintain stability and return to port under her own power, the destroyer. Laffey provided perhaps the most dramatic early validation of fog nozzle effectiveness. April 16, 1945, off Okinawa. Laffey endured one of the most intense kamikaze attacks of the war. In just 80 minutes, the destroyer was crashed by 6 kamikaze aircraft and hit by 4 bombs. Each impact started fires. The crew fought these fires continuously throughout the attack, using fog nozzles to suppress flames, even as additional kamikazes struck the ship. The fires were fed by ruptured fuel lines, burning debris, and aviation gasoline from crashed aircraft. Traditional solid streams would have scattered this burning fuel, likely spreading fires faster than they could be contained. Fog patterns extinguished burning gasoline without spreading it, used minimal water, preventing flooding that could have capsized the heavily damaged destroyer, and cooled spaces threatened by fire spread. Laffey survived with 32 killed and 71 wounded. The ship was heavily damaged but remained afloat and was eventually repaired. Her survival under such intense attack with fires burning across multiple locations simultaneously demonstrated that properly trained damage control, parties using effective equipment, could save ships even under extreme circumstances. Laffey's experience became legendary in the fleet, proof that fog nozzles and damage control training worked even in the worst conditions imaginable. The battleship South Dakota provided another validation. In June 1944, a bomb hit during operations in the Marianas penetrated to a handling room where ready ammunition for anti-aircraft guns was stored. The bomb explosion ignited powder charges, starting a fire that threatened to reach the main magazines below. If those magazines detonated, South Dakota would have been destroyed. Firefighting teams attacked the fire using fog nozzles with extension applicators, directing fog through openings in the deck to reach flames below. The fog cooled the space and generated steam that displaced oxygen, smothering flames before they could reach the main magazines. Simultaneously, other parties used fog to cool the magazines themselves, reducing temperatures and preventing sympathetic detonation. The fire was controlled in 35 minutes, and South Dakota continued operations. Traditional methods might not have allowed close enough approach to prevent magazine detonation. The carrier Hancock survived a kamikaze hit on April 7, 1945, off Okinawa. The hit penetrated to the hangar deck and exploded among parked aircraft. The explosion ignited aviation gasoline and started fires that spread through the hangar. DC parties used both direct fog application and indirect fog through ventilation systems to attack flames simultaneously from multiple directions. The hangar deck sprinkler system had been damaged by the explosion, so fog nozzles provided the primary firefighting capability. The fire was controlled in 70 minutes. 62 men were killed and 71 wounded, but Hancock remained operational and continued launching strikes within hours. These incidents and dozens of others validated Burke's transformation of naval firefighting. Ships that should have been lost were saved. Casualties that would have been catastrophic were reduced to manageable levels. The fleet's operational capability was maintained even under intense enemy attack. Word spread through the fleet about fog nozzle effectiveness, building enthusiasm and confidence for the techniques Burke had championed. The ultimate test. USS Franklin, the USS. Franklin had already proven the value of fog nozzles before her near destruction in March 1945. On October 30, 1944, while operating off the Philippines during the Battle of Leyte Gulf, Franklin took her first major hit. A Japanese kamikaze aircraft evaded the combat air patrol and crashed through the flight deck, penetrating to the hangar deck, where it exploded among 33 aircraft that were being prepared for strikes. The explosion was catastrophic. Aviation gasoline from ruptured aircraft fuel tanks ignited instantly, creating a fireball that filled the hangar. Bombs and rockets stored on the aircraft began cooking off, adding explosions to the fire. Ready ammunition for aircraft guns detonated, sending shrapnel throughout the hangar space. Within minutes, fires were burning across the entire hangar deck. Franklin's damage control parties had been trained in Burke's methods. They responded immediately with fog nozzles, establishing a coordinated attack on the fires from multiple directions. Teams positioned themselves at hangar deck access points and directed fog patterns into the space, cooling superheated gases and creating conditions where direct entry became possible. Other teams used extension applicators to reach areas too hot for direct approach, directing fog through damaged sections of the hangar deck and ventilation openings. The fog patterns prevented fire spread to adjacent spaces while teams attacked the main body of fire. The combination of multiple fog streams working together, creating steam that displaced oxygen while cooling structures, proved devastatingly effective against the inferno. The battle to save Franklin that October day lasted 2 and frackbanta 2 hours. Temperatures in the hangar exceeded 2,000 degrees F, hot enough to melt aluminum components and warp steel beams. Traditional solid streams would have been ineffective at those temperatures. The water would have flashed to steam before reaching the seat of the fire, providing little cooling effect. Fog patterns, already optimized for steam generation, provided maximum cooling efficiency even at extreme temperatures. The damage control parties worked in shifts, rotating men out as they reached the limits of heat exhaustion, bringing in fresh teams to maintain continuous firefighting. They advanced systematically, section by section, cooling spaces, extinguishing fires in areas that had been brought under control while preventing reignition. By 1500 hours, all major fires were out. By 1700 hours, temperature reduction allowed damage assessment teams to enter the hangar, and hotspots had been extinguished. 56 men were killed and 60 wounded in the October attack, most in the immediate aftermath and initial explosion. But Franklin survived and was able to withdraw under her own power. The carrier returned to combat operations within 3 weeks after temporary repairs were made at Ulithi. The official damage report credited effective damage control training and fog nozzle application as critical factors in saving the ship. This October experience provided crucial lessons for Franklin's crew. They identified areas for improvement in communication and coordination. They learned their training worked under combat conditions. They gained confidence that even severe fires could be controlled with proper techniques. This experience would prove invaluable 5 months later, when Franklin faced damage that should have destroyed her. The ultimate test of Burke's transformation came on March 19, 1945, when USS Franklin suffered damage that should have destroyed her. The carrier was operating 50 miles off the Japanese coast, part of Task Force 58, conducting strikes against airfields on Kyushu in support of the Okinawa invasion. At 07:08 hours, a single Japanese dive bomber penetrated low through heavy overcast, evading radar detection until it was too close for effective anti-aircraft fire. The bomber dropped 2 bombs that struck Franklin's flight deck and hangar deck in the worst possible locations at the worst possible time. 31 aircraft were spotted on the flight deck, fully fueled and armed with rockets and bombs, prepared to launch for the first strike of the morning. 22 more aircraft filled the hangar deck below, similarly fueled and loaded. The total aviation gasoline aboard these 53 aircraft exceeded 15,000 gallons. The ordnance they carried included Tiny Tim rockets, 500 Dalu text alveolar bombs, and thousands of rounds of ammunition. The first bomb penetrated the flight deck near the center line and detonated on the hangar deck. The explosion instantly ignited every aircraft in the hangar space. Aviation gasoline sprayed across the deck as fuel tanks ruptured, creating a lake of fire that spread throughout the 400 text FT dollars long hangar. The intense heat immediately began cooking off ammunition and ordnance on the burning aircraft. The second bomb, near the number 3 elevator, penetrated to the gallery deck, detonating in crew berthing areas and instantly killing dozens of men while starting fires on 3 decks. Ruptured fuel lines fed additional gasoline into the fires. The explosion also damaged critical systems, including communication systems, electrical distribution, and fire mains. Within 2 minutes, a dozen Tiny Tim rockets broke loose from their mounts on burning aircraft. These massive 11 non-text long rockets, each carrying a 138 text $, warhead, became unguided missiles ricocheting around the hangar deck. They exploded when their warheads hit hard enough to detonate them, penetrated through to adjacent spaces, and struck bulkheads. Each explosion started new fires and sent shrapnel throughout nearby compartments. Larger ordnance started detonating as fires reached rockets and bombs on aircraft. Machine gun ammunition began cooking off by the hundreds of thousands of rounds. The sustained fusillade of bullets tore through thin bulkheads, wounded or killed anyone in the vicinity, and made the hangar deck a death trap. The casualties in the first 10 minutes were horrific. The initial explosions instantly killed approximately 300 men, flight deck crews spotting aircraft, hangar deck personnel preparing planes, and sailors in berthing areas near the second bomb impact. Hundreds more were wounded, many critically burned. Dozens jumped into the sea or were blown overboard to escape the inferno. The ship's medical facilities were quickly overwhelmed. Franklin's propulsion system was lost when engineering spaces filled with smoke, forcing their evacuation. The ship went dead in the water, drifting 50 miles from the Japanese coast with fires burning across 4 decks. Radio communications were destroyed, preventing calls for assistance. The list developed as water from ruptured fire mains and accumulated firefighting efforts reached 13 dwells on Circe on the starboard side, threatening to increase further. In these desperate circumstances, Lieutenant Commander Joseph T. O'Callaghan, the ship's Catholic chaplain, and Lieutenant Donald A. Gary, an engineering officer, organized the firefighting effort that would save Franklin. O'Callaghan moved through the ship, gathering anyone still able to fight. Storekeepers, clerks, cooks, anyone not already engaged in treating casualties or fighting fires. Gary organized rescue parties to reach men trapped below by smoke and fire. They grabbed fog nozzles and advanced into conditions that would have been impossible with traditional equipment. Many of the ship's fire mains were ruptured, meaning water pressure was far below normal levels. Electrical power was lost, eliminating pumps that normally maintained pressure. The hangar deck sprinkler system had been destroyed. The damage control parties had to work with whatever water pressure they could get, using portable pumps supplemented by bucket brigades in areas where mains were completely failed. The training program created a common culture across the fleet. Sailors trained at different bases, using identical techniques, spoke a common language of damage control. Officers could assume standardized capabilities and coordinate effectively even when ships from different squadrons operated together. This standardization extended to equipment maintenance, tactical procedures, and even terminology, used to describe firefighting operations. Layman and the civilian. Legacy Burke's transformation of naval firefighting occurred alongside parallel developments in Coast Guard firefighting doctrine. Lloyd Layman, who had pioneered indirect fog application techniques as a civilian fire chief before the war, was commissioned as a commander in the Coast Guard and placed in charge of the firefighting school at Fort McHenry in Baltimore. Layman conducted extensive research on fog nozzle applications using the Liberty ship Gaspar de Portola as a test platform. His experiments documented optimal application techniques, fog patterns, and droplet sizes for different fire conditions. He published his findings in Fire Engineering magazine in February 1945, providing scientific validation for the techniques Burke had championed based on practical experience. After the war, Layman returned to civilian fire service as chief of the Parkersburg, West Virginia Fire Department. He applied the shipboard fog techniques he had perfected during the war to structural firefighting, revolutionizing how municipal fire departments fought fires in buildings. His 1950 presentation, Little Drops of Water, at the Fire Department Instructors Conference, demonstrated how indirect fog application could extinguish structure fires more effectively than traditional solid stream attacks. Layman's work ensured that lessons learned in naval combat would transform civilian firefighting globally. The techniques Burke championed for saving ships became standard practice for saving buildings. The fog nozzle became ubiquitous in fire departments worldwide, valued for its effectiveness and versatility across multiple fire types. The enduring principles Burke continued serving through the immediate post-war period and the war's end, refining fog nozzle techniques and training instructors. In July 1947, he was appointed chief of the New York City Fire Department, a position representing the pinnacle of municipal firefighting leadership. He took office on August 1, 1947, but immediately retired from the position upon his appointment. The circumstances of Burke's brief tenure as chief remain somewhat unclear in historical records. Fire Engineering magazine reported on August 1, 1947, that Chief Harold Burke immediately retired upon his appointment. The position remained vacant until Peter J. Loftus was appointed as the new chief on August 1, 1948. During his brief time in the position, Burke influenced the FDNY to adopt training methods developed for the Navy, including standardized tactical approaches and realistic fire training props. Burke's post-war life remains largely undocumented. No death date has been located in accessible records, and his later years remain a mystery. He disappeared from public view after his retirement, leaving behind a legacy measured in ships, saved and lives preserved rather than in honors or public recognition. Fog. Nozzles remained standard equipment in the United States Navy for decades following their adoption. While new technologies emerged and specific designs evolved, the fundamental principles Burke championed, that fine water droplets provide superior steam generation and cooling, compared to solid streams, remained foundational to naval firefighting through the remainder of the 20th century. The next major evolution in naval firefighting came following the catastrophic USS Forrestal fire on July 29, 1967, in the Gulf of Tonkin. A Zuni rocket accidentally fired across the flight deck, striking a parked aircraft and rupturing fuel tanks. The resulting explosions and fire killed 134 airmen and sailors and injured 161. The disaster revealed continuing gaps in damage control capabilities, particularly regarding foam firefighting systems for aviation fuel fires. FFF, aqueous film-forming foam, had been patented by the Navy in 1966, but was not yet deployed fleet-wide. The Forrestal disaster prompted mandatory implementation of AFFF systems throughout the fleet and a complete overhaul of aviation firefighting procedures. Yet fog nozzles remained essential equipment, valued for effectiveness and versatility against multiple fire types. AFFF supplemented fog nozzles rather than replacing them. Through the 1970s and 1980s, fog nozzles remained standard damage control equipment aboard all naval vessels. Successive generations of sailors learned the same basic techniques Burke had introduced, fundamentally unchanged in principle, but adjusted for new ship designs and evolving fire threats. The fog nozzle endured because it worked, because it was versatile enough for multiple applications, and because the physics of heat absorption through water surface area remained constant regardless of technological changes elsewhere. Lessons. For military innovation, Burke's influence extended far beyond the Navy. Municipal fire departments worldwide adopted fog nozzles following the war, driven by returning veterans who brought naval firefighting experience into civilian fire service and by demonstrations of effectiveness in naval applications. The adoption was steady but gradual. Fire departments that had resisted fog nozzles before the war found the evidence from naval combat compelling. Industrial firefighting, particularly in refineries and petrochemical facilities, embraced fog nozzle technology for superior performance against flammable liquid fires. Industrial fire brigades adopted both equipment and techniques developed by Lehman and Burke, recognizing that petroleum fires in industrial facilities presented challenges similar to those aboard ships. Fire service training evolved to incorporate lessons learned in naval combat. Fire academies built training props modeled on naval designs, creating realistic fire conditions where students experienced smoke, heat, and conditions approaching actual emergencies. The emphasis shifted from classroom theory to hands-on experience, from lectures about firefighting to actually fighting fires under controlled conditions. The principles Burke championed became fundamental to fire science education globally. Fire engineering curricula taught the advantages of maximizing water surface area, the physics of steam generation and heat absorption, and the tactical applications of solid streams versus fog patterns. What had been rejected as radical innovation in 1941 had become accepted wisdom by 1950, taught in fire academies worldwide as established doctrine. The story of Lieutenant Harold J. Burke and the fog nozzle illuminates broader truths about institutional change and military innovation. Several patterns emerge that remain relevant for modern military organizations facing doctrinal and technological challenges. External expertise is vital. Transformative change often originates outside military institutions from civilians who bring different expertise and perspectives. Burke succeeded not because he invented fog nozzles. They existed before his advocacy. But because he brought municipal firefighting experience into a military context and persisted despite institutional resistance, his civilian expertise provided insights that purely internal development would likely never have achieved. Demonstrated superiority is key. Overcoming institutional resistance requires demonstrated superiority under realistic conditions. Burke's theoretical arguments and verbal explanations convinced no one. His carefully controlled demonstration, showing objective measurements of fog nozzle performance compared to traditional methods, provided evidence that could not be dismissed. The demonstration format, quantified results, comparable conditions, realistic fires, was critical to building credibility. Internal champions are necessary. Innovation requires internal champions with sufficient authority to mandate change. Burke's demonstrations and expertise were necessary but not sufficient. Admiral Cochrane's support was essential to forcing fleet-wide implementation and overcoming bureaucratic resistance. The combination of internal authority and external expertise proved decisive. Standardized training is essential. Effective implementation requires standardized training that proves new techniques can be taught systematically. Burke did not just train a few elite units. He created a scalable training program that produced hundreds of instructors who trained thousands of sailors to consistent standards. This standardization ensured that fog nozzle adoption translated into actual capability, rather than just equipment distribution.